The study of rigid body rotation reveals a complex interplay of forces and energy that governs everything from spinning tops to the stability of planetary systems. By looking at these motions through the lens of vector calculus and potential fields, we can understand the underlying structure of rotation without relying on complex equations. Kinematic foundations of rotation. The motion of a rigid body rotating around a fixed point is defined by its velocity and acceleration at every point within the object. The velocity field describes a perfect circular flow, where the speed of any given point depends on how far it is from the axis of rotation. Acceleration in this system is more complex, consisting of two distinct components. The Euler acceleration, which occurs when the object speeds up or slows down its spin, and the centripetal acceleration, which constantly pulls points inward toward the center of rotation. Vector calculus analysis. To understand the shape and behavior of these motion fields, we analyze their divergence and curl. The velocity field of a rotating rigid body is incompressible, meaning that the material is neither created nor destroyed as it moves. It simply flows in a closed loop. The local rotation rate within this field, known as vorticity or curl, is directly proportional to the overall spin rate of the body. When we examine the acceleration field, we see a different story. The acceleration vectors tend to point inward, creating a negative divergence. This reflects the constant compressive effect required to keep the rigid body together against the outward pull of rotation. Furthermore, the rotation of the acceleration field itself is tied directly to the rate at which the object's spin is changing over time. Centrifugal potential and work energy. A profound insight from the sources is that the pseudo-forces felt in a rotating frame are conservative. This means that the work done moving an object between 2 points in a rotating system depends only on its distance from the center, not the path it takes to get there. Moving away from the center of rotation is mathematically identical to falling down a potential hill. In this environment, the Coriolis force, which deflects moving objects, is unique because it does zero work. It changes an object's direction but never its speed. Consequently, energy is perfectly conserved between the object's radial motion and its centrifugal potential energy. This potential energy is essentially the stored version of the tangential kinetic energy the object would have if it were fixed to the rotating frame. Orbital stability and the centrifugal barrier. This concept of potential energy provides the ultimate explanation for orbital stability in space. A planet is caught in a tug-of-war between two competing forces, the inward pull of gravity and the outward push of its own centrifugal potential. These two forces create a potential well, or valley. At great distances, gravity is the dominant force, acting as a tether that prevents the planet from flying away. However, as the planet gets closer to the Sun, its spin rate increases to conserve angular momentum, causing the outward centrifugal push to grow much faster than the gravitational pull. This creates an impassable centrifugal barrier that acts as a physical shield, preventing the planet from ever crashing into the center. A stable orbit is simply a planet sloshing back and forth within this protective valley, trapped between the gravitational tether and the centrifugal shield.